we now explain the details of the revised simplex algorithm using this example. The example problem is to maximize 6x1 plus 8x2 subject to x1 plus x2 less than or equal to 10, 2x1 plus 3x2 less than or equal to 25 and x1 plus 5x2 less than or equal to 35. We have 3 inequalities and all 3 are of the less than or equal to type. So, we first convert these inequalities to equations by adding slack variables plus x3 equal to 10 instead of this plus x4 equal to 25 and we add a third slack variable plus x5 is equal to 35. So, now x3, x4, x5 being slack variables with a plus 1 coefficient and they appear in only one constraint. So, they can qualify to be the basis. So, we start the simplex algorithm with x3, x4 and x5 as basic variables. So, we say xb set of basic variables is the set x3, x4, x5 and they will have values 10, 25 and 35. So, they take values 10, 25 and 35. There are 2 non-basic variables which are x1 and x2. Since x3, x4 and x5 are the basic variables, the basis matrix B is a 3 by 3 matrix corresponding to 3 basic variables and the basis matrix B will be the matrix 1 0 0, 0 1 0, 0 0 1 which is I, which is an identity matrix. Since the basis matrix is an identity matrix, B inverse is also the identity matrix. Now, in order to check whether this present basis is optimal, we need to look at the 2 non-basic variables which are x1 and x2 and find out if any one of them can enter the basis. To do that, we have to find out C1 minus Z1 for variable x1 and C2 minus Z2 for variable x2. Now, Cj minus Zj is equal to Cj minus Ypj. So, C1 minus Z1 is equal to C1 minus Yp1. Y is the value of the dual and P1 is the vector corresponding to the variable x1 in the original problem. Therefore, P1 will be 1 2, P2 will be 1 3. C1 is the objective function coefficient of variable x1 which is 6 and C2 is 8. So, this will become 6 minus y into 1 2 where y is 1 2 P1 is the vector corresponding to variable x1. So, therefore, that is the vector 1 2 1. So, y into the vector 1 2 1. Y is the value of the dual variables. Y is given by CBB inverse. CB is the objective function coefficients of the basic variables. The 3 basic variables x3, x4 and x5, all 3 of them are slack variables. So, CB is 0. So, 0 0 0 into B inverse is I, which we have shown here. B inverse is equal to I. Therefore, y is equal to 0 0 0. Therefore, C1 will become 6 minus 0 0 0 into 1 2 1 which is 6. In a similar manner, C2 minus Z2 will be 8 minus 0 0 0, which comes from the value of y, multiplied by P2, which is the vector corresponding to variable x2, which is 1 3 and 5. So, 1 3 and 5. So, this will be 8 because y is 0. Now, both C1 minus Z1 and C2 minus Z2 are positive. So, based on the maximum coefficient rule, variable x2 will enter the basis because C2 minus x2 is 8, which is bigger than C1 minus Z1. So, variable x2 will enter the basis. Now, in order to find the leaving variable, we need to find the column vector, column corresponding to variable x2, and that is given by P bar j is equal to B inverse Pj, and B inverse is I. Therefore, P bar j will be equal to Pj, which is 1 3 and 5. Pj corresponds to P2, which is from here 1 3 and 5. Now, theta is the ratio between the right hand side value and the corresponding P bar j. So, we should take the minimum of 10 divided by 1, 25 divided by 3, 35 divided by 5. Another way of saying is that we find out minimum theta such that 10 minus theta is greater than or equal to 0, 10 minus 1 into theta is greater than or equal to 0, 25 minus 3 theta greater than or equal to 0, and 35 minus 5 theta greater than or equal to 0. Now, this would give us theta equal to 10, this would give us theta equal to 25 by 3, this is 7, 7 is the smallest of the 3, therefore, theta will be equal to 7, and this variable will leave the basis, which means the third variable will leave the basis. So, x5 will leave the basis. So, at the end of the first iteration, we have understood that we started with x3, x4, x5 as basic variables, and we found out the optimality of this basis and realized that this basis is not optimal because both of these are positive, which meant that variable x2 will enter the basis and variable x5 will leave the basis. So, in the next iteration, the set of basic variables xb is now x3, x4 and x2, because variable x2 has now replaced variable x5. Now, the corresponding right hand side values can straight away be given. We have found out from here that theta equal to 7, and the third variable is the one that leaves. So, in the next iteration, the variable x2 will take a value theta, which is 7, while the rest of the variables will take the corresponding value when we substitute theta into these two expressions. So, 10 minus theta is 3, 25 minus 3 theta is 4. So, we will have x3 equal to 3, x4 equal to 4 and x2 equal to 7. We can even verify this. X2 equal to 7, x1 plus x2 plus x3 is equal to 10. So, 7 plus 3 is 10. 3x2 plus x4 is 7 into 3, 21 plus 4, 25. 5x2 plus x5, 5x2 is 35 plus 0 is 35. So, we now have this as the basis, and we now have to find out whether this basis is optimal. So, in order to do that, we need to look at the two non-basic variables, which are x1 and x5, and find out their Cj minus Zj values. Now, before we find the Cj minus Zj values, we first have to find out the value of the dual, which is y. So, y is given by Cb B inverse. Cb is the objective function coefficient corresponding to the basic variables. So, this has 0, 0 and variable x2 has 8. So, y will be 0, 0 and 8 into B inverse. Now, B inverse, another way of looking at it is, instead of saying y is equal to CB B inverse, you can always say YB equal to CB. Ordinarily, what we would do is, we now know that this basis matrix is a 3 by 3 matrix corresponding to x3, x4 and x2. So, the basis matrix B will be corresponding to x3, x4 and x2. So, 1 0 0, 0 1 0 and corresponding to x2 would be 1 3 and 5. So, one way of finding out this y is by taking this basis matrix B, inverting it in the usual way, either by finding out first the determinant and the cofactor and the adjoint and then getting B inverse, or by inverting B in other ways such as Gauss-Jordan method or Gaussian elimination or any of these methods. But what we are going to do now is something different. We are not going to directly and explicitly invert B, but we are going to indirectly invert the basis matrix B. So, what we will do now is, we simply call this B as B1, which is the basis matrix corresponding to iteration number 1. The earlier B, which was the starting iteration, is now called B0. Now, what we are going to do is to say that B1 is equal to B0 into E1, where E1 is called an eta matrix, and eta matrix is also a 3 by 3 matrix. The difference is that one column of the 3 by 3 matrix is a non-identity column, and that non-identity column is exactly the column corresponding to P bar j. So, in our case E1 will become, it is a 3 by 3 matrix. Since the third variable left the basis, the third column of the eta matrix E is a non-identity column. So, the other two columns are 1 0 0, 0 1 0, and the third column is P bar j, which is 1 3 and 5. It happens that B1 is equal to E1, and in fact, in all the first iteration B1 will always be equal to E1. Later we will see that it changes. So, now B1 is equal to B0 into E1. So, in order to find out y, we should find out y B1 is equal to CB. So, y B0 E1 is equal to CB. B0 is I. So, y E1 is equal to CB. Now, y is a vector. So, y is now written as y1, y2, y3, because there are 3 constraints, there are 3 basic variables in the primal, there will be 3 dual variables for y. So, y1, y2, y3 into E1, which is given here 1 0 0, 0 1 0, 1 3 5 is equal to CB, which is 0 0 and 8. Now, the nice thing about writing this way is that the computations are much simpler, because the first equation will be 1 into y1 plus 0 into y2 plus 0 into y3 is equal to 0. This is a 1 into 3, this is a 3 into 3. So, the resultant is a 1 into 3. So, y1 plus 0 y2 plus 0 y3 is 0, which would give y1 as 0. From the second one, y1 0 y1 plus 1 y2 plus 0 y3 is equal to 0 would give us y2 equal to 0. y1 plus 3 y2 plus 5 y3 is equal to 8 would give us y3 is equal to 8 by 5. So, y value is 0, 0 and 8 by 5. So, now with the value of y that we have obtained, we will now go back and find out the Cj minus Zj corresponding to the two non-basic variables which are x1 and x5. So, we have to find out C1 minus Z1, which is C1 is 6 minus y P1. So, y is 0, 0, 8 by 5 into P1. P1 comes from the original matrix, which is the column corresponding to variable x1 in the original matrix, which is 1, 2 and 1. So, C1 minus Z1 is 6 minus this into 1, 2 and 1, which is 6 minus 0 into 1 plus 0 into 2 plus 8 by 5, 6 minus 8 by 5, which is 22 by 5. Now, C5 minus Z5 is C5 variable x5 is a slack variable, therefore, C5 is 0 minus y 0, 0, 8 by 5 into P5. P5 comes from here. So, P5 is 0, 0 and 1 because variable x5 appears only in this constraint with the coefficient of 1. It does not appear in these two constraints. So, we have 0, 0, 8 by 5 into 0, 0, 1, which is minus 8 by 5. So, Cj minus Zj of the two non-basic variables, non-basic variable x1 gives us a Cj minus Zj positive value. For variable x5 it is a negative value. There is only one positive Cj minus Zj, therefore, variable x1 will enter. Now, once variable x1 will enter, we now have to find out the leaving variable. So, in order to find out the leaving variable, we need to find out P bar 1 is equal to B inverse P1. Once again, we do not have B inverse explicitly computed. So, we pre-multiply by B to get B times P bar 1 is equal to P1, because B into B inverse will give I. So, I into P1. Now, this B is nothing but B naught into E1. So, we will have E1 P1 bar is equal to P1. B naught is also the identity matrix. So, this will reduce to E1 into P1 bar is equal to P1. Now, E1 is known, so E1 is here. So, E1 is 1 0 0, 0 1 0, 1 3 5 into P1 bar is what we want to find out. So, we simply call it as some A B C that we want to find out. P1 comes from the original matrix and P1 is here, P1 is 1 2 1. Once again, because of the very nature of the eta matrix, it is easy to compute this A, B and C. So, what we will do now is we will take P bar 1 is equal to 0 into A plus 0 into B plus 5 into C, which is the third equation. 0 into A plus 0 into B plus 5 into C is equal to 1. So, C is 1 by 5. From the first equation, 1 into A plus 0 into B plus 1 into C is equal to 1. So, A plus C is equal to 1, C is 1 by 5. So, A is 4 by 5. From the second equation, 0 into A plus 1 into B plus 3 into C is equal to 2. So, B plus 3C is equal to 2. So, B plus 3 by 5 is equal to 2. So, B is equal to 2 minus 3 by 5, which is 7 by 5. So, we have now computed P bar 1, and having computed P bar 1, we now have to find out theta. The right hand side values are here. So, theta is such that you have to find out minimum theta such that 3 minus 4 by 5 theta is greater than or equal to 0. 3 comes from here, 4 by 5 comes from here. So, 3 minus 4 by 5 theta is greater than or equal to 0. 4 minus 7 by 5 theta is greater than or equal to 0. And 7 minus 1 by phi theta is greater than or equal to 0. So, this will give us theta equal to 12, theta is equal to 15 by 4, sorry, this would give us theta is equal to 15 by 4, this would give us theta is equal to 20 by 7, and this would give us theta is equal to 35. So, here theta value is 5 into 3 15 by 4. So, this is 15 by 4, this is 20 by 7 and this is 35. Now, 20 by 7 is the minimum value of theta. So, this variable, which is the second variable, will leave the basis. So, this variable is the leaving variable. So, what we have done here is from this basis we found out that this basis is not optimal because C1 minus Z1 is positive. So, variable x1 enters, and when variable x1 enters we found out that variable x4 leaves. So, we go to the next iteration where the basis changes. So, from this basis we know that variable x4 is leaving and variable x1 is entering. So, we will have x3, x1 and x2 as the set of basic variables. So, now the values of these three are given by, the second one was the one which left the basis with theta equal to 20 by 7. So, this variable x1 will take 20 by 7, the other two will take the corresponding values. So, this will become 3 minus 4 by 5 into theta. So, 3 minus 4 by 5 into 20 by 7, so 4 16. So, this would give us 21 by 7 minus 16 by 7, which is 5 by 7, and the third one will be 7 minus 20 by 7 into 1 by 5 is 7 minus 4 by 5, which is 7 minus 1 by 5 theta. So, 7 minus 1 by 5 into 20 by 7, which is 7 minus 4 by 7, which is 45 by 7. A quick check again would give us x1 plus x2 plus x3 is equal to 10, 45 plus 20, 65 plus 5, 70 divided by 7 is 10, 2x1 plus 3x2 plus x4 is 0. So, this is 25, 2x1 is 40, 3x2 is 135. So, 175 by 7 is 25, and x1 plus 5x2 plus x5. So, 5x2 is 225 plus 20 is 245 by 7, which is 35. So, this has been checked. Now, for this set of basic variables, we now need to find out whether this is optimal, and to find out whether this is optimal, we have to find out the Cj minus Zj corresponding to the two non-basic variables, which are x4 and x5. So, we have to find out C4 minus Z4, and we have to find out C5 minus Z5. Now, before we do this, we need to find out the value of the dual, which is y. So, dual y is given by yb is equal to Cb. Now, we now call the basis corresponding to this as B2. So, yb2 is equal to Cb. Now, B2 will be written as B1 into E1. So, y B1 E2 is equal to Cb, where E2 is a suitably defined eta matrix. B1 is already known to be B0 into E1. So, we will have y E1 E2 is equal to Cb. Now, we already have E1 written here, E1 is this. So, E1 we just copy down for our reference. So, E1 is 100, 010 and 135. Now, E2 is another eta matrix with one column not identity column. From here we understand that the second variable is the leaving variable. So, the second column in E2 will be the non identity column. So, E2 will be 1 0 0, 0 0 1, which is the third column, and the second column is the non identity column, and that second column is given by p bar 1, which is computed here as 4 by 5, 7 by 5 and 1 by 5, as 1 by 5. Now, we know that y E1 E2 is equal to C B. So, first what we do is we call this y into E1 as some u. So, we write u into E2 is equal to C B. So, u is written as U1, U2, U3 into E2 is 1 0 0, 4 by 5, 7 by 5, 1 by 5, 0 0 1 is equal to C B. C B is the objective function coefficients of the basic variables x3, x1, x2. So, 0, 6 and 8. So, this will be 0, 6 and 8. So, from this we can find out that u1 plus 0 u2 plus 0 u3 is equal to 0. So, u1 is 0, 1 into u1 plus 0 into u2 plus 0 into u3 is 0. From the third, 0 into u1 plus 0 into u2, 1 into u3 is 8. So, u3 is 8. From the second one, 4 by 5 u1, 7 by 5 u2 plus 1 by 5 u3 is equal to 6. So, 7 by 5 u2 plus 8 by 5 is equal to 6. 7 by 5 u2, 6 minus 8 by 5. So, this is 22 by 5, from which u2 is 22 by 7. So, now we know this u. Now, come back to this and say y into E1 is equal to u. So, you will have y1, y2, y3, which is y, into E1, which is 1 0 0, 0 1 0, 1 3 5 is equal to y E1 is equal to u. So, this is equal to 0, 22 by 7 and 8. Now, from this y is equal to 0 into y1 plus 0, 1 into y1 plus 0 into y2 plus 0 into y3 is 0. So, y1 will be 0. 0 into y1 plus 1 into y2 plus 0 into y3 is 22 by 7. So, 22 by 7. 1 into y1 plus 3 y2 plus 5 y3 is equal to 8. So, 3 y2 is 66 by 7 plus 5 y3 is equal to 8. So, 66 by 7 plus 5 y3 is equal to 8. So, 5 y3 is equal to minus 10 by 7, y3 is minus 2. So, you have 0, 22 by 7 and minus 2 coming in as the values of the 3 variables. Now, having found out y is 0, 22 by 7 and minus 2, with this value of y, we need to find out the Cj minus Zj of the 2 non-basic variables x4 and x5. So, C4 minus Z4 will be equal to C4 is 0 minus YP4. So, which is 0 minus 0, 22 by 7 minus 2 into P4 is from here, which is 0 1 0. So, this will be minus 22 by 7 and C phi minus Z phi is equal to 0 minus 0 22 by 7 minus 2 into 0 0 1 which is plus 2. So, now C phi minus Z phi is positive, therefore, variable x 5 will enter the basis. So, this basis is not optimal and variable x 5 will now enter this basis. Now, in order that variable x 5 enters the basis, we need to find out the leaving variable from this. Now, to find out the leaving variable, we need to in order to find out the leaving variable, we need to find out P bar phi is equal to B inverse P phi, pre-multiplying by B inverse, pre-multiplying by B, we get B into P bar phi is equal to P phi. Now, this B is B2, so B2 is equal to B1 into E2, B1 is B0 into E1, so we will have E1 E2 P bar 5 is equal to P 5. Now, we already know the values of E1 and E2, E1 and E2 are matrices which are here. So, what we do now is we simply call this E2 into P bar 5 as some V is equal to P 5, where this V is a vector. So, some V equal to P 5. So, from this we get E1 is 1 0 0 0 1 0 1 3 5, and we could simply call this V right now as some ABC will be equal to P 5, which is 0 0 and 1. P 5 is 0 0 1 because in the original problem variable x 5 comes only in constraint number 3. Because of the nature of the eta matrix, it becomes easy to compute A, B and C. So, from this we can easily get V is equal to the third one 0 into A plus 0 into B plus 5 into C is equal to 1. So, C is 1 by 5. Now, 1A plus 0B plus 1C equal to 0 would give us A equal to minus 1 by 5. 0A plus 1B plus 3C equal to 0 would give us B plus 3C equal to 0, B plus 3 by 5 is equal to 0. So, B is equal to minus 3 by 5. Now, once we know V equal to this, we now go back here, we have already written E2 into P 5 bar as V. So, E2 is here. So, 1 into 1 0 0 4 by 5 7 by 5 1 by 5 0 0 1 into P bar 5 is now written as some ABC is equal to minus 1 by 5 minus 3 by 5 plus 1 by 5. So, once again by the very nature of the eta matrix, we can get P bar phi by a simple substitution process as 0 into A plus 7 by 5 into B plus 0 into C is minus 3 by 5, from which B is equal to minus 3 by 7. So, this gives us 7 by 5 B is equal to minus 3 by 5. So, B is equal to minus 3 by 7. From this A plus 4 B is equal to minus 1 by 5. So, A minus 12 by 35 is equal to minus 1 by 5. So, A minus 12 by 35 is equal to minus 7 by 35, which is minus 1 by 5. Therefore, take it to the other side, A will be equal to plus 5 by 35, which is plus 1 by 7. Now, to find out C, 1 by 5 B plus C is equal to 1 by 5. So, 1 by 5 B is minus 3 by 35 plus C is equal to 1 by 5, minus 3 by 35 plus C is equal to 7 by 35. So, taking it to the other side, you get 10 by 35, which is 2 by 7. So, this is 2 by 7. So, now we have found out P bar 5, and once we know P bar 5, we can find out theta. Now, the corresponding values are 5 by 7, 20 by 7 and 45 by 7. So, the corresponding value of theta will be such that 5 minus 1 by 7, 5 by 7 minus 1 by 7 theta is greater than or equal to 0 from the first one, 5 by 7 minus 1 by 7, 20 by 7 plus 3 by 7 theta greater than or equal to 0, the plus comes because of the minus sign here, and 45 by 7 minus 2 by 7 theta greater than or equal to 0. This would give us theta equal to 5. This would give us theta equal to any value because we have a positive coefficient here, and this would give us theta equal to 45 by 2. Therefore, this is the variable that leaves. So, variable x3 is the variable that leaves, and the basis now changes. So, the basis now changes to xb equal to, we have found out now that variable x5 enters the basis and variable x3 leaves the basis. So, we have x5, x1, x2 as the basis, and the corresponding values will be here. This was the variable that left. So, this will have theta value which is 5. Now, at theta equal to 5, 20 by 7 plus 15 by 7 is 35 by 7, which is 5, and at theta equal to 5, this will become 45 by 7 minus 10 by 7, which is also 5. So, we now have another basic feasible solution with x1 equal to 5, x2 equal to 5 and x5 equal to 5. Now, once again we need to check whether this basis is optimal, and in order to do that we have to find out Cj minus Zj corresponding to the two non-basic variables, which are x3 and x4. And before we find out C3 minus Z3 or C4 minus Z4, we need to find out y, which is the value of the dual. So, yb is equal to Cb. Now, y, this b is called B3. So, B3 will be B2 into E3, B2 is B1 into E2, B1 is B0 into E1 and B0 is I. So, putting all of them together we will get y into E1, E2, E3 is equal to Cb. We right now have values of E1 and E2 which are written here. So, we need to write the value of E3. So, E3 is another eta matrix, which is an identity matrix with one column not being the identity column. Now, from this we found out that the first variable actually left the basis, therefore, the first column is the non-identity column. So, the other two columns will be 0 1 0 and 0 0 1, and the first column will be corresponding to P bar 5, which we found out as 1 by 7 minus 3 by 7 and 2 by 7. So, 1 by 7 minus 3 by 7 and 2 by 7, because we wrote this out of p bar 5. So, if p bar 5 is 1 by 7 minus 3 by 7 2 by 7, we would have got 5 minus 1 by 7 theta, 20 by 7 plus 3 by 7 theta, and 45 by 7 minus 2 by 7 theta. So, this is our E3. Now, using this E1, E2, E3 and CB, we should now find out y. So, what we first do is we call this whole thing as u and say u into E3 is CB. CB is the objective function coefficient of the basic variables, which is 0, 6 and 8. So, this is 0, 6 and 8. So, we now substitute E3. So, U1, U2, U3 into 1 by 7 minus 3 by 7, 2 by 7, 0, 1, 0, 0, 0, 1 is equal to 0, 6, 8, from which u is equal to. Now, from the third one, 0 into u1 plus 0 into u2 plus 1 into u3 is 8. So, u3 is 8. 0 into u1 plus 1 into u2 plus 0 into u3 is equal to 6. So, u2 is 6. 1 by 7 u1 minus 3 by 7 u2 plus 2 by 7 u3 is equal to 0. So, 1 by 7 u1 plus minus 18 by 7 plus 16 by 7 is equal to 0. So, 1 by 7 u1 minus 2 by 7 is equal to 0. 1 by 7 u1, this is minus 18 by 7 plus 16 by 7. So, minus 2 by 7. So, 1 by 7 u1 minus 2 by 7 is equal to 0, from which u1 is equal to 2. So, once we know u1 is equal to 2, we now go back and find out the other one. So, this is called u1. So, y E1 E2 is equal to u1. So, we now call this as v E2 is equal to u1. So, v will be v1 v2 v3 into E2 1 0 0, 4 by 5 7 by 5 1 by 5 0 0 1 is equal to 0 2 6 and 8, because we found out that u is 2 6 and 8. Now, once again by the very nature of the eta matrix, we can get V is equal to V1 plus V2 plus V1 plus 0 V2 plus 0 V3 is equal to 2, from which V1 is 2. Again 0 V1 plus 0 V2 plus 1 V3 is 8. So, we get 8. Second one is 4 by 5 V1, which is 8 by 5 plus 7 by 5 V2 plus another 8 by 5. 1 by 5 into 8, 8 by 5 is equal to 6. So, 8 by 5 plus 8 by 5 is 16 by 5. So, 6 minus 16 by 5 is 14 by 5. So, 7 by 5 V2 is equal to 14 by 5, therefore, V2 is 2. So, now we have found V. Now, we again go back, we have written y into E1 as V. So, we write y1, y2, y3 into E1, which is from here 1 0 0, 0 1 0, 1 3 5 is equal to 2 2 and 8, from which y is equal to, once again by the very nature of the eta matrix, y1 plus 0 y2 plus 0 y3 is 2. So, y1 is 2, 0 y1 plus 1 y2 plus 0 y3 is 2. So, y2 is 2. This alone is y1 plus 3 y2 plus 5 y3 is 8, y1 is 2, 3 y2 is 6, 6 plus 2 8, y3 therefore is 0. 2, 2 and 0 is the value of y. Now, we can actually even verify the value of y from here. We also know that at any point the value of the objective function of the primal and the dual are the same. So, primal has x1 equal to 5, x2 equal to 5, substituting this is 30 plus 40 70, and the other dual is 2, 2 and 0, 2, 2 and 0 would give us the same 70. So, it is another verification that the dual that we computed is correct. So, once we know that this is the value of the dual, we now go back and there are two non-basic variables x3 and x4. So, we need to find out C3 minus Z3, which is 0 minus y 2 2 0 into P3 1 0 0, which is minus 2. Now, y is 2 2 0, y into P3, P3 comes from here corresponding to variable x3. So, here the coefficient is 1, 0 and 0. Similarly, P4 will be 0, 1 and 0 because this does not appear in the first equation. So, C4 minus Z4 is equal to 0 minus 2 2 0 into 0 1 0, which is minus 2. So, Cj minus Zj corresponding to both the non-basic variables are negative, there is no entering variable and the algorithm terminates. So, the algorithm terminates now with the objective function value of 70 with x1 equal to 5, x2 equal to 5, z is equal to 70, and from the dual y1 is equal to 2, y2 is equal to 2, y3 equal to 0. So, 20 plus 50 is also 70. So, the algorithm terminates. So, this is how the revised simplex algorithm works. Now, on the face of it, it looks much more computationally intensive or laborious compared to the tabular form. The tabular form was much more comfortable, largely because we are used to the tabular form. Now, the only change that actually happened between the tabular form and this way of doing it is the fact that B inverse was not explicitly computed either using the determinant cofactor adjoint method or by using Gauss-Jordan, which we did in the tabular form. Now, if we look at this very carefully, in this iteration to find out y, we had something like y into E1 into E2 into E3 equal to CB, which means we have to do this 3 times to get y. In case this was not optimal, then to find out the entering variable p bar, we need to again do it 3 times. So, in the third iteration, it will be 3 multiplications to get y and perhaps another 3 multiplications to get the p bar. So, which means in the 100th iteration, we will be multiplying it 100 times in the forward direction to get y and another 100 times in the reverse direction to get a p bar. Therefore, the question naturally arises is this a very efficient method? Because apart from this, everything else was the same, and more importantly, we also need to store the E1, E2 and E3. We do not need to store any other thing. Obviously, we will be storing this, but in addition to that, we only need to store E1, E2 and E3. So, from a storage point of view, it is said that we normally will not store it as a 3 by 3 matrix. E1 will be stored only as this vector 1, 3 and 5, and a simple identification that this vector is in the third column. This one will be stored as 4 by 5, 7 by 5, 1 by 5 and 2, which means this first 3 are in the second column and so on. So, you do not end up storing a large matrix, instead you store only a vector for every E, that you need store only the vector for every E. Now, the other question is this laborious process of forward multiplications and reverse multiplications efficient? Incidentally, the answer is yes. Now, for the normally small sized problems that we work out, we will know that the tabular form is much better than this. But as the problem size increases, say we have linear programming problems with 100 constraints or more, then we realize that actually this way of calculating y and p bar in the forward and backward directions is actually much faster. So, for the simple problems 2 by 2, 3 by 3 that we normally encounter in a classroom, the tabular method is still very efficient. The moment we get into solving larger sized linear programming problems, typically more than 100 constraints, this method is found to work much better than the tabular method. So, in terms of speed, this method is much better, and one of the things with which we started this course is to find out how do we make the simplex work a little faster. So, we zeroed in on the fact that if the most important thing in the simplex is actually the matrix inversion. If we do the matrix inversion well by a better method and do it faster, automatically time taken per iteration will come down. The number of iterations we have already said we could do based on the largest coefficient rule or any suitable rule. So, the revised simplex method helps in actually bringing down the computation of the simplex algorithm, because the time taken per iteration comes down when the problem size is large. Now, the method that we have seen particularly to invert is called the eta factorization of the basis. Which we have seen to convert the basis as a product of several eta matrices, and we also use this method called product form of the inverse, where to find out the inverse we try and multiply these eta matrices once in the forward direction and once in the reverse direction. Forward direction to get y and in the reverse direction to get p bar. So, this is a brief description of the revised simplex algorithm through a numerical illustration. The next thing that we would like to see in linear programming is another important aspect of linear programming. Now, in the next important aspect of linear programming, we also wish to see how well we can actually make the linear programming problem work if constraints in linear programming are of a certain type. So, we take a simple example to start that, and the example that we will do is to maximize (8x1 plus 3x2) subject to 3x1 plus x2 less than or equal to 7, 2x1 minus x2 less than or equal to 8, 2x1 plus 3x2 less than or equal to 20, x1 less than or equal to 2, x2 less than or equal to 6, xj greater than or equal to 0. So, let us consider a linear programming problem of this type. Now, right now this linear programming problem has two variables x1 and x2, and it appears that this linear programming problem has 5 constraints, 3 constraints involving both x1 and x2, 3x1 plus x2 less than or equal to 7 and so on. The last 2 are constraints of the type x1 less than or equal to 2 and x2 less than or equal to 6. Now, this problem can be solved using the revised simplex that we just now saw in this lecture. The thing is, if we use the revised simplex or even the tabular form of the simplex, we will have 5 constraints, and in every stage or every iteration we will be inverting a 5 by 5 matrix. Now, a much closer look at these 2 constraints would tell us that these constraints involve only one variable, and therefore, these constraints are not treated as constraints, they are called bounds on the variable. So, they are bounds on the variable. Now, the question is, do we have to look at this as a 5 by 5 problem and solve, or can we simply take these bounds outside, look at it only as a 3 constraint problem, and then at every stage suitably incorporate or bring these bounds back into the solution. If we end up doing that, then we have reduced the number of constraints. So, we already saw in this lecture that the biggest aspect of an iteration of simplex is the matrix inversion. So, if we do not treat this as a bound and treat it separately, we end up having 5 constraints and we end up inverting a 5 by 5 matrix in every iteration. Whereas, if we pull these two things out and solve the resultant 3 constraint problem, also making sure that these are satisfied, but solving it as a 3 constraint problem, then we end up having a 3 by 3 matrix to invert in every iteration. So, can simplex be modified in such a manner that if there are bounds, these bounds are not treated as constraints, these bounds are taken separately and only the resultant constraints are solved, which also means that a constraint is a constraint when it involves more than one variable. If it involves only one variable, then the constraint becomes a bound. So, can simplex be adapted to problems which has bounded variables? So, we will now address what to do with simplex, particularly when simplex has bounded variables, and therefore, the algorithm that we will see is called simplex algorithm for bounded variables. As I said, these two are the bounded variables. So, we will simply take these variables outside, treat them as bounds, write them separately as x1 less than or equal to 2 and x2 less than or equal to 6. Now, this bounded method can be solved using the revised simplex algorithm. We can also solve it by the normal algebraic method, which with a motivation to simplex, not the typical algebraic method where we evaluate all the basic solutions, but we can solve it by the algebraic way. So, how we do the simplex method for bounded variables in using the algebraic method, we will see in the next lecture.